Okay, so we're finishing up 12.3. We left off and we were going to talk about the expected value. All right, so the expected value is the average value of all the different outcomes. All right, it's kind of confusing what expected value is, but we do use it a lot in real life. You find the expected value by multiplying each outcome by its probability and then adding each together. Expected values, like you could use them for like the lottery. You know, when is it good to play the lottery? Different things like that. So basically, let's say I was having a raffle in this class, and let's see, there's 1, 2, 3, 4, 5, 10, there's 15 of you today. All right, so your probability of winning, if you each had one ticket, was 1 out of 15. Okay, so what if I said you had to pay $1 and you were only going to win $1.50? Do you guys think you'd play? No, you'd most likely probably lose your dollar, right? It wouldn't be really worth it. But let's say I upped the ante and I was like, oh, I'm going to give $100 to the winner. Do you guys think you'd play then? Yeah. So expected value has to do with when is it smart for you to play the game. So my husband doesn't really understand this because, you know, with the lottery, he's like, oh, you know, my probability of winning, I know it's not good, but I'm going to win $1 million. So I should play. But his probability of winning is less than 1 over 1 million. So he's basically going to probably lose his dollar in the ticket, like the $1 or $2 now that it costs for the ticket. Makes sense? So occasionally, mathematicians will play the lottery. Occasionally. This was a big day when, if you guys remember over spring break, when the Mega Millions made it like 640,000 or 640 million is what you could win. All my mathematician friends were like, I'm actually playing the lottery. This is a big day. Because then it was actually, you know, kind of a good chance. Not that you would win, but I mean, it made it seem like it was worth paying the money. So it's kind of weird. It's like you still have the same chances of winning, but when is it worth playing? Very strange. Okay, so number one, so suppose there's a raffle at university, and students are selling 300 raffle tickets. The 3 prizes are worth $50, $100, and $200. Each time a name is drawn, it is put back into the box. Therefore, you could win all 3 prizes. Raffle tickets are $5 each, should you buy a ticket. Okay. So let's see. So we have 300 total tickets. Let's say that you cannot, I didn't say this in here, but we probably need to say it. You could only buy 1 ticket. So each person can only buy 1 ticket. But their parents can buy them and all that. So 300 people will probably buy the different tickets. Okay, the 3 prizes are worth $50, $100, and $200. Okay, what's your probability of winning? 1 out of 300 for the first draw, right? Okay, then you put it back in the box. Is it still 1 out of 300? Yeah, because you put your name back in the box. Okay, so your expected value is the prize times its probability plus the next prize times its probability plus the next prize times its probability. Okay, so your probability of winning the first thing is 1 out of 300. The prize is $50. The next prize is $100. And the last prize is $200. Now, this is almost the probability. Let me show you what happens. So let's go ahead and add these together. So 50 out of 300 is 1/6 plus 1/3 plus 2/3. So 1/6 plus 1/3 plus 2/3 is 1 and 1/6, so 7/6. Okay, but what could also happen? So you could win all these different things, but what else might happen? You may lose your money, right? So your raffle ticket costs $5. Your expected value is, this number is like, this isn't quite the expected value, I should say the expected winning. I'm going to say winnings there. Is 1.17, so $1.17. That's what 7/6 is of $1. Okay, so you're expected to win about $1.17. Should you pay $5? No. If it was $1, yeah, you should play. You might win 17 cents, basically. All right, but so this means that our expected value is the amount you paid. So you paid $5 minus that $1.17. So that'd be $3.83. Oh, negative. Dang it. Switch these early in the morning. Because you're paying the... So it's a negative amount. Okay, you don't want for your expected value to be negative. Okay, that's when you don't play the game. Okay. I used to do this all the time when I was in college. Like, I'm a super nerd, but you know, you go to these different carnivals. Like Evansville always has this big like festival. So we would go to the festival each year, and they'd always have raffles. And I'd be like, oh, you know, there's this car, or there's never really a car, but they'd have different things that you could win. And I would always like estimate how many tickets were in there, and I'm like, ooh, my chances don't look so good. But if they did look good, I'd buy a ticket. So, okay. Next up, so it says the table below shows the probability distribution of the payoff on a $1 scratch-off lottery ticket. So I don't know if this is true or not, but find the expected value and interpret the result. Okay, so your probability of getting $0 is 0.91176. So that means your payout times your probability, and you're just going to keep doing payoff times probability, payoff times probability, payoff times probability. You can do ... if you're tired of writing it all. Okay. This is the amount of money that you are expected to win. So these are like your expected winnings. What are we going to do at the end? What do we need to subtract out? The $1, so what you paid. Okay, so let's go ahead and do this. So the first thing's 0 anyway, so that's gone. So 5 times 0.06 plus 10 times 0.02. So keep multiplying on your calculator. When you add them all together, you get 0.78. So your expected value, you're paying $1 no matter what. So you 0.78 minus that $1. So you get negative 22 cents. So would you play the scratch-off game? No. So it's best not to play that game. I will say sometimes it is nice with the scratch-off tickets. Sometimes you can make a lot. My dad made $20,000 last year on a scratch-off ticket. That was a big day in his life. It was like a week before he retired, so it was pretty nice. But usually not so good. So. All right. So 12.3 stars on conditional probabilities. So this section's not in your textbook, but this is definitely a probability type topic. It's not hard. It'll be fine. All right, so we talked about dependent events before. Do you guys remember what was an example of a dependent event? Something that depends on something else, right? So let's go back to the raffle. What would be an example of a dependent event with a raffle?
If you didn't put the person's name back?
Yeah, if you didn't put the person's name back, right? So if I drew Gabby's name first, and then I didn't put her name back, and then I drew Andrew's name, right? So Andrew's probability would have been a little bit better than the first draw, because now we've lost Gabby's name, right? Okay, so that would be dependent events. Okay, oh, I guess I say that in here. So it says, for instance, if we have a raffle and names are not put back in the box, we could find the probability that Trent wins the prize first and then Brian wins the second prize. You could compute the probability that Trent wins the first prize and then multiply by the probability that Brian wins the second prize, given that Trent's name is out of the box. Okay, conditional always says given, usually. So given that something else has happened. All right, so suppose we want to find the probability that events A and B occur. Okay, when we did our tree before, remember with the candies, you guys had this on your homework. So you could say, okay, well the probability that Brian's name is drawn would be like, let's say there's 20 people, it'd be 1 out of 20. If I select Brian's name, then the probability that Trent's drawn is 1 out of 19, right? There's one less person in the box. So the probability that A and B occur, so that Brian's name is picked first and then Trent's, or Trent's and then Brian's, doesn't matter. I guess you could do it this way too. Is the probability, so if I said Trent and then Brian, like I said here, would be the probability that Trent wins first, so 1 out of 20, times the probability that Brian wins, given that you've already started down this path. So given that Trent has already won, so that'd be 1 over 19. So a tree usually helps on these conditional probabilities. Okay, so this little line here means given. So the probability of B given that A has already happened. So it says if you wanted to find the probability that B occurs given that A has already occurred, so that would be the probability that B occurs given A. Kind of looks like a division sign, it's not, it's just a straight up and down line. You simply divide P of A to the other side, so you have the probability of P and B over the probability of B. Oh, probability of A, sorry. I'm doing this in the opposite order I usually do. A. Okay. You might see this. Probability of A intersect B. So A and B. So that little upside down U means and. Okay, I think on your homework I used that notation. Okay, so let's say I give my class 2 tests. 25% of the class got an A on both tests, so that's the A and B thing. And 42% of the class got an A on the first test. What percent of those who got an A on the first test also got an A on the second test? Okay, so we need to think about how to set this up. So we're gonna we could just use 1 and 2, I guess, but we'll let A equal the first test and B equal the second test. And that would be getting a first test is an A, and second test is an A. When I say first test, second test, I mean you get an A on them. All right, let's write down the different things we know. So first we know that 25% of the class got an A on both tests. So that means the probability of A and B is 0.25. So they got an A on both for the first test and the second test. All right, and then it says 42% of the class got an A on just the first test. So that's the probability of A is 0.42. So it says what percent of those who got an A on the first test also got an A on the second test? So this is asking, find the probability of getting an A on the second test given that they already got an A on the first test. Does that make sense? Okay, that's what we're trying to find. So the probability that you got an A on the second test, given that you already got an A on the first test. Okay, this ends up being the probability of A and B all over the probability of B. The way I always memorized the formula when I did this is I thought of, oh crap, A. See, I'm doing it wrong now. I always thought of this as divided by A. That's how I remembered, oh, I have to have the divided by P of A on the bottom. Now you can do it the opposite way. You can say the probability of A given B is the probability A and B all over probability of B. Does that make sense? So it does depend what the second thing is. That's what goes on the bottom. Okay, so do we know these numbers? So A and B is the 0.25. You're going to divide by 0.42. So the probability that they get an A on the second test, given that they've already gotten an A on the first test, is 0.595. So almost 60%. Wouldn't that make sense that if they've already scored well on the first test, they're probably going to score well on the second test? They probably have a better chance of scoring well on the next test. Okay. So I'd say round to 3 decimals. All right, so let's try this one. So a jar contains black and white marbles. 2 marbles are chosen without replacement. Okay, so we don't put them back. The probability of selecting a black marble and then a white marble is 0.34. The probability of selecting a black marble on the first draw is 0.47. What is the probability of selecting a white marble on the second draw, given that the first marble was black? Okay, so this is probability of getting a white marble on the second draw given that the first was black. So black, oh no, probability of white given that you had a black one on the first draw. That's what we're asked to find. Okay, so the probability of selecting a white and then a black divided by probability of black is what we need. So white and then black is 0.34. The probability of selecting a black marble is 0.47. So we do 0.34 divided by 0.37. Oh, 0.47. So you should get 0.723. Okay, think about our tree. So if I drew the tree, this would be the probability of selecting a black marble and then a white. This whole stem, so going this whole direction here, would be 0.34. Oops. All right, and then it says the probability of selecting a black marble on the first draw is 0.47. So this is 0.47 here. So what is the probability of selecting a white marble on the second draw given that the first one's already black? So we're asked to find this probability. Okay, so that's what we're doing. So you're taking your total answer and you're dividing out by the first number to get the middle number. Okay, so number 3, it says the probability that it is Friday and that a student is absent is 0.03, so 3%. Since there are 5 school days in a week, the probability that it's Friday is 0.2. So in that you have school, right? What is the probability that a student is absent given that today is a Friday? Okay, so probability that they're absent, I'll write it out this time, given that it's Friday. So that would be the probability that they're absent and it's Friday divided by the probability that it's Friday. So remember, whatever I had on the second is now on the bottom. That's Friday. Okay. So I know the probability that it's Friday is 0.2, so 1/5. The probability that it's Friday and a student is absent is 0.03. So do 0.03 divided by 0.2. So you get 0.15, so 15%. Is this making sense? Okay. All right, you guys try 4 and 5. So 4 and 5. Okay, so it says in the United States, 56% of all children get an allowance and 41% of all children get an allowance and do household chores. What is the probability that the child does household chores given that the child gets an allowance? So we'd set up probability of chores given that they get an allowance. So you can write it out if you want to keep track of what's what. So that would be the probability of chores and allowance. Or you can use your little upside down U for and. All over the probability that they get an allowance. Okay, so we said 41% of all children get an allowance and do chores. So that's the 0.41, that's the numerator. And then 56% of children get an allowance. So 0.56. So we do 0.41 divided by 0.56. So you get 0.732. Did you guys get that? Good. All right, it says at UHS, 18% of all students play soccer and basketball, and 32% of all students play soccer. What's the probability that a student plays basketball given that the student plays soccer? So probability of basketball and soccer, all over the probability of soccer. So we said 18% play both, 32% play only soccer. So that's 0.563 if I round to 3 decimals, or 0.5625 you could have as well. Did you guys get that?
Yeah.
Okay. Now know that these can be a little tricky. Like at the beginning of your homework, I give you the probability of A, the probability of B, and the probability of A and B. So like I'll give you this, and this. And I ask you to find 2 things. I ask you to find the probability of A given B and the probability of B given A. So think about how you would do each one. So if I had A given B, what would you do? On the numerator you have probability of A and B, right? And then you divide by probability of B, okay? For part B, if I had probability of B given A, you would do probability of A and B divided by probability of A, right? Okay, so just know that I may ask that. And then occasionally you are asked to find this number. So like the probability that they do chores and allowance when you're given these 2 things. So occasionally you might have to do that. Okay, so just kind of look for those different things.